Thank you very much for the introduction. So today I would like to talk about the threat of quantum computers or current cybersecurity. In my talk, I will firstly briefly review how we use cryptography today. Afterwards, I will try to explain what threat quantum computers represent for our current infrastructure for secure communication. And then I will talk about what measures are currently undertaken to prepare for this threat. Firstly, I will talk about the NIST PQC standardization process, which is the largest project directed in this direction. And then I will talk about how we try to contribute to this topic at this university, at this faculty where we are right now. So let's talk about how we use cryptography today. So basically today we use two types of cryptography. First type of cryptography is called symmetric cryptography. Examples include the encryption scheme AES or the message authentication codes, for example, HMAC. And these cryptographic primitives are very, very efficient, but they require users. If two users want to encrypt data with AES, for instance, they need to share some secret key beforehand. So this is a drawback for symmetric cryptography, that the users need to share a secret key. And to overcome this drawback, we also have asymmetric cryptography, which we use, for instance, to establish the secret key, usually by Diffie-Hellman key exchange. By Diffie-Hellman key exchange, we establish secret key, which we later use in AES. But we also use asymmetric cryptography for digital signatures, like RSA signatures, also we have asymmetric encryption scheme like RSA encryption scheme, and we also have key encapsulation mechanisms, KEMs, which are another way how users can exchange a secret key, which they can later use for symmetric encryption. So, yeah, the asymmetric cryptography is less efficient than symmetric cryptography. So, but the upside is that asymmetric cryptography does not require the shared secret key, which symmetric cryptography requires. So, as I said, we usually use them together jointly. And here's an example of such usage. This is example which comes from a situation when we ordinary people browse the internet. Then usually our web browsers, they communicate with the server through HTTPS protocol, and they use this protocol to exchange the encrypted data with the server. And the HTTPS protocol works in such a way that firstly, asymmetric cryptography is used, usually the Diffie-Hellman key exchange, to establish shared secret between the web browser at our computer and the server, which runs the web page. And afterwards, this shared secret key is used with symmetric cryptography to encrypt data that we want to exchange with the server, with the web page. So it's very common to use both asymmetric and symmetric cryptography together. And the asymmetric cryptography today, the cryptosystems that we use today in asymmetric cryptography their security relies on hardness of one of these two problems that are highlighted here. First, it's prime factorization problem. The security of RSA relies on hardness of factorizing large numbers into the product of prime numbers. And the other problem current asymmetric cryptography relies on is the problem of discrete logarithm. For instance, the Diffie-Hellman key exchange relies on the hardness of this problem. So we can use RSA or Diffie-Hellman key exchange securely only because humanity has no efficient algorithms for solving these problems. Solving prime factorization for large numbers, it's hard. We don't have any efficient, any polynomial algorithm which would solve prime factorization, and similar is the case of discrete logarithm. So I said that humanity has no efficient algorithms to solve prime factorization or discrete logarithm problem. To be more precise, I should have said that humanity has no efficient classical algorithms for solving these problems. By classical algorithms, I mean algorithms that are designed to run on classical computers. But humanity has an efficient quantum algorithm for solving these problems. So let's talk about that. That brings us to the thread of quantum computers. And so, although we don't have a classical algorithm for solving prime factorization and discrete logarithm, already since 1994, it is known that if we had a large quantum computer, then we could solve prime factorization problem or discrete logarithm problem efficiently using so-called Shor's algorithm. It's named after its inventor, Peter Shor. And what this means is that if we had a large quantum computer, then we could break most of asymmetric cryptography which is used today. So we could break all the communication on the internet, all the encrypted communication on the internet, basically. So this is quite scary prospect, and well, maybe it's appropriate to ask this question if we should panic. And fortunately, we don't have to panic. The situation is not that bad because currently no large quantum computers exist, but progress is being made in their development. Some small quantum computers already exist, but there are scalability problems. So in 2021, there was this poll done among researchers in quantum physics, and these 46 researchers were involved in this poll, and they were asked the questions. They were asked about what they think is the likelihood of having a quantum computer which will be able to break RSA 2048, that's the version of RSA that we use today, in just 24 hours. They were asked what they think is the likelihood of this happening in different time horizons. First time horizon is 5 years, then 10 years, then 15 years, 20 years, 30 years. And what you can see in this graph is that if they were asked, like, if they believe that there will be such powerful quantum computer that it could break current cryptography in 5 years, then most of them found it quite unlikely. Like half of them said that they believe that the likelihood is very, very low, less than 1%. But if they were asked whether they believe such computer will be around in 30 years, then the situation was quite the opposite. Like more than half of them thought that the likelihood of such event is more than 95%. So from this, we can see that the experts in the field, they think that the quantum computers, large quantum computers, are coming. and they believe they will be here in 30 years, well, at least majority of the experts. So what this means for us cryptographers, because I'm a cryptographer, is that we cryptographers, we need to develop new standards for asymmetric cryptography. And so we need to replace RSA because it's based on prime factorization, and prime factorization will be solvable by quantum computers. And every asymmetric cryptosystem has to be based on some hard problem, but it no longer can be a prime factorization problem. We have to devise new asymmetric cryptosystems which will be based on different problems, and such problems which will be hard to solve even on quantum computers. So cryptosystems with this property are called post-quantum cryptosystems. And just a little disambiguation. So post-quantum systems, they belong to post-quantum cryptography. And so, as I said, this is an area where we try to design cryptosystems which are resistant against attacks by quantum computer. So these cryptosystems are resistant against, let's say, quantum technology, but they use only classical technology. These cryptosystems are designed to run on our computers which we have today, on our classical computers. So we designed them with the aim to replace RSA or Diffie-Hellman with something which would also resist attacks of quantum computers. So this is very different from the area of quantum cryptography, which deals with design of cryptosystems which use quantum phenomena. So they are not designed to run on our everyday computers that we use today. They require some special hardware where some quantum mechanics can be measured. An example of quantum cryptography is quantum key distribution, which was, I believe, mentioned several times in the previous talk. So these are two very different areas with different goals. So I mostly work in the first one, in post-quantum cryptography, and that's what I'm going to talk about in this talk. So we have a number of post-quantum cryptosystems which we already believe should be can run on our today computers and should be resistant against attacks of quantum computer. And we have actually various branches for such cryptosystems. Some such cryptosystems come from lattice-based cryptography, some come from code-based cryptography, and there are also some other areas of cryptography which produce such cryptosystems. And so we have already some cryptosystems about which we believe are post-quantum, but now there is this question like when should we transition to such cryptosystems? And the transitioning process, the cryptographic community believes should start right now, because if you encrypt something today, then you want it to remain secret for some period of time. This period of time is here in this figure denoted by X. And for instance, if you encrypt today and you encrypt with let's say RSA, and you want your data to remain secure for 15 years, but in 10 years quantum computer arrives, then you are in trouble. So we need to have we need to make this transition to post-quantum cryptography before quantum computer arrives, and well before, because usually we want to have the data encrypted for some time. So far I've talked about the implications of quantum computer for asymmetric cryptography. In the beginning, I said that there's also symmetric cryptography. Fortunately, the impact of quantum computers on symmetric cryptography is much less significant. There is so-called Grover's algorithm, which can theoretically make some attacks on symmetric cryptography more efficient, but the gain from using Grover's algorithm on quantum computer is not so huge as, for instance, gain of using Shor's algorithm, which breaks prime factorization. So it is therefore widely believed that the current symmetric cryptosystems like AES can be still safely used in the quantum era. Maybe only we will need to switch to larger keys. But remember, for symmetric cryptography, we still need a method how to secretly share the secret key. And for that, we need asymmetric cryptography. So we still, the problem of developing post-quantum asymmetric cryptosystems is still very significant. And the largest effort in this direction today is the NIST PQC standardization process, which started in 2016, and in 2016, NIST, which is American Institute of Standards and Technology, as most of you, I'm sure, know, and they launched this process in 2016, and the aim of this process, as the title of the process says, is to create new standards for asymmetric cryptography, which will be resistant against attacks by quantum computers, so to create post-quantum asymmetric cryptographic standards. And this process has two categories. First is they want to create new standards for encryption or key establishment. And the second category is they want to create new standards for digital signatures. So this process is pressed to be quite transparent and open, I believe. And so NIST invited researchers from all around the world to send suggestions for post-quantum cryptosystems, to send their submissions. Everyone could do it. There were no restrictions. And so in 2017, when there was a deadline for sending these candidates, NIST received 82 of them, and 69 were deemed to be complete, and they were accepted as first-round candidates. So the process started with 69 candidates for post-quantum cryptosystems, and they were all made public, including their implementations. And the cryptographic community was free to analyze these cryptosystems, to publish papers on them, to find their weaknesses. And this process is actually still ongoing, but it already produced some results. So until 22, 3 rounds of the NIST competition have passed, and through these rounds, NIST iteratively trained the number of candidates. So firstly it was 69, then I believe it was somewhere around 20, then 15, and in July 22, NIST already announced that they selected first 4 candidates from those original 69, which NIST they selected first 4 candidates for standardization. So in July 2022, NIST already said that, okay, we're going to prepare standards for 4 post-quantum cryptosystems. I will talk more about them on next slides. In addition, in July 2022, NIST also announced that there will be round 4 of the competition, and they selected 4 other candidates from those original 69 to advance into the round 4. And NIST also called for additional competition for digital signatures. So soon after July 2022, additional competition for post-quantum digital signatures started. And I will talk about each of these 3 points on the next slides. So let's talk about maybe the most important point, the first standards. So in July 2022, NIST announced that the primary algorithms NIST recommends to be implemented for most use cases are Crystal Kyber, which is used for key establishment. Like it can replace the Diffie-Hellman key exchange in some sense. And Crystal Lithium, that's their recommended post-quantum digital signature algorithm. So they decided, they announced that they will standardize these two, and they recommend they use for most use cases. In addition, they also announced that they will standardize 2 additional signature schemes. One is called Falcon and one is called Sphinx Plus. On the next slides, I will talk about their benefits and their weaknesses, their drawbacks. So firstly, let me talk about Crystal Kyber. This is the only post-quantum crypto system which is used for key establishment, which NIST decided to standardize so far. The size of its public key and its ciphertext is very favorable when taking other post-quantum crypto systems into account. So NIST finds it suitable for most applications. Also, the encapsulation and decapsulation mechanisms are very fast, so reasonably fast. And NIST has already published a draft version of the standard for Crystal Kyber. It's available freely on the internet, on the webpage, which you can find among the resources in this presentation. And so that's Crystal Kyber, the only algorithm they so far selected for standardization, which deals with the exchange. Their favorite digital signature is Crystal Lithium. It's based on lattices, similar as Crystal Kyber. Actually, it comes from almost the same team of authors. Not exactly the same, but there's a big intersection between the team of authors of Crystal Lithium and Crystal Kyber. It uses the heuristics, which is called Fiat-Shamit transform. It's a method how to create digital signatures. And again, NIST finds that parameters like public key, signature speed, and signature size very favorable, and finds it suitable for most applications. And similarly, as in case of Kyber, this has already published a draft version of the standard. So, as I said, the Crystal Lithium is not the only digital signature that this decided to standardize. There are 2 more. One is called Falcon. It is again lattice-based, but it uses different paradigm than Crystal Kyber. I said that Crystal Lithium. Pardon me. I said that Crystal Lithium is based on Fiat-Shamir transform. Falcon uses the hashed and signed approach, which is also the approach the RSA uses. Again, NIST finds its parameters very reasonable and finds it suitable for most applications. It has even smaller signatures than Crystal's Lithium. So in this metric, it's even better than Crystal Lithium. But at least the problem which I find most serious with Falcon is that it's much more difficult to implement than Crystal Lithium. That stems from the fact that Falcon uses floating point arithmetic, and As a result, no draft version of the standard has been published yet. So it appears to be much more difficult to standardize Falcon. But NIST wants to do it in a year, but that's unofficial information. It was a private estimate from somebody from the NIST. He said that if he believes that the draft standards will be published in a year for Falcon. And apart from Falcon and Dilithium, NIST also decided to standardize Sphinx Plus, and that's a very different animal compared to Falcon and Crystal's Dilithium. It is no longer a lattice-based digital signature, it is a hash-based digital signature. Its main positive is that it has very strong security guarantees, like the security assumptions made in Sphinx Plus are such that majority of cryptographers believe really has big trust in these assumptions. Its main negative is that the parameters and the performance of Sphinx Plus is not as good as in case of Falcon and Dilithium. It's the signature algorithm is slower. It produces larger signatures, but it's basically a very conservative choice for digital signature algorithm. It's something which people really trust is secure, but it doesn't have as good performance as Crystal Dilithium and Falcon. There are more questions about the security of Crystal Dilithium and Falcon than there are about Sphinx Plus. So the draft version of Sphinx Plus is available. It was published in August 2023. It's a draft version of the standard for Sphinx Plus. It was published by NIST at the same time as the draft version of standards for Dilithium and Kyber. So these are the 4 algorithms that NIST has already decided to standardize, but NIST would like to have a broader family of standards available. And so far we have in the family of standards we have cryptosystems based on lattice cryptography and on hash based cryptography. But NIST would also like to have something based on code-based cryptography, because again, code-based cryptography it uses different other security assumptions than lattice based cryptography or hash-based cryptography. So NIST also announced round 4 of their competition, and into this round 4 they selected for other cryptosystems that they find promising. All of them are KEMs, which is abbreviation for key encapsulation mechanisms. So all of these 4 cryptosystems they are used for key exchange, and NIST says that they would like to standardize at least one of them. And since July 2022, it was already the big news appeared, and that was that one of these algorithms, this site was broken, was badly broken. It's NIST doesn't advise to use it at all. So basically, there are 3 remaining algorithms, and NIST will probably standardize at least one of them. All of them are code-based. Psych was isogeny-based. It's completely a different algorithm from these 3. And so as we stand now, NIST decided to standardize one algorithm for key encapsulation and 3 algorithms for digital signatures, and they have 3 other candidates for key encapsulations that were on the previous slides. But NIST would also like to standardize some additional digital signatures algorithm, and that's why. And they didn't like any of the original 69 candidates for digital signatures to advance into round 4. So they decided to announce a new call for digital signatures, which started recently. So NIST was sent NIST received suggestions for more digital signatures recently from academic community, and again they published it on their webpage together with implementations. And in the next years, these new digital signatures will be again analyzed, and NIST decides whether they want to standardize any of them or not. So this PQC standardization, at least at NIST, appears that it will continue in the upcoming years, and that there will be more algorithms standardized, not just those 4 which I mentioned previously. And I think I skipped this slide, and this is quite important. So I said I was talking about the first 4 algorithms that NIST decided to standardize. So I said that the 3 of them have their draft version of standards already available, and it's available for public comment until November 22, 2023. So it's available for public comment for 1 more month. And NIST plans to publish the final standards for these 3 algorithms in 2024. So the final version of the standards should be available pretty soon. And okay, so that's what I wanted to say about the NIST PQC standardization. And now I would like to talk about how we try to contribute to the research on post-quantum cryptography at ASTU, at this faculty. So there are several people who work in this area, including 2 professors, an associate professor and 2 assistant professors. All of us are based here in this building. And the topics we are interested in are firstly security analysis of post-quantum cryptosystems. We also found a weakness in one of the cryptosystems that was submitted in the NIST competition. And the other thing we are very much interested in is the topic of secure implementation of post-quantum cryptosystems, because it's one thing to have a good abstract mathematical algorithm, which in theory is secure, but other way is to implement it securely. If you don't pay much attention to its implementation, then it can happen that the implementation, when will leak some information about this secret key or secret message when the implementation, when the computations are performed on some hardware. So this information that can leak, that can be, for instance, the time it takes to decrypt, or it can be the sound that the hardware produces during decryption, or it can be variations in its power consumption. Okay, thank you. And attacks which use such leaks are called side channel attacks, and so we are interested in these attacks and how to avoid them. For instance, we studied acoustic side channel attacks. These were invented when we during the NATO project which we participated in by our colleagues in Tel Aviv University. We were able to repeat them at in this building, and this is our apparatus. This is a computer which performs. This computer performed RSA decryption. Here is a microphone which recorded the sound during the decryption, and here is a computer which was used to analyze the sound. And if the RSA is not implemented correctly or carefully, then it can happen that just by recording the sound you can break it. So we are interested about such attacks and countermeasures against such attacks on post-quantum cryptography. This is a huge field, and yeah, we worked on these NATO projects when these attacks were invented, and this NATO project was also awarded the NATO Science Partnership Prize 2018 for the best NATO project in the area of cyber defense in the last 10 years. And since then, we have worked on other NATO projects and currently are working on a third NATO project, all in the same area, similar area. So thank you very much. I'm sorry for taking a bit too long. If there is time for questions, I'm happy to answer.
I mean, it's for 3 questions. So
okay.
Go ahead.
So the first question is whether there are any open source implementation of PQ algorithms in some of the programming languages. Yes, there are actually many of them, and when researchers wanted to submit something into the NIST competition, which I talked about, they had to also submit the implementation, and this implementation is free, publicly available. So. So, for instance, I talked about NIST Kyber, crystals Kyber and crystals Lithium, and if you Google it, then you will find a web page, and which was for these cryptosystems, which was created by its authors, and the web page also has a link on their GitHub when they have their free implementation. So. Yeah, it's available, and usually the implementations are in C, just plain C. That's how it's usually done in cryptography. How much qubits are this? This one is very okay. The first question which appears here is very difficult to answer. I don't want to go into that, but the second I can answer very quickly. Yes, SIGE was broken mathematically. There were basically a new mathematical algorithm was found to attack the problem. SEDH problem is called the name of the problem, which the security of SIGE rests on. So yeah, it was badly broken, and it was broken mathematically.